Yeah, number 7.
Yeah.
Number 7, number 7, number 7. Oh, that was just putting in the truth table. So you have the PQ columns.
Yeah.
And then, so number 7 and number 2, they're pretty much just an algebra question, right?
Yeah, but number 2, the statement is false, if I'm correct.
I think, yeah, I don't remember offhand, but I think so. So those two problems were just replacing P's and Q's with T's and F's and just using the rules of and or.
Yeah, I did it, but I question myself sometimes, but I think number 2 is false, if I'm not mistaken.
I'm pretty sure that's correct.
All right.
So those were like what I consider arithmetic questions, right?
Yeah.
Numbers. So they shouldn't have been, yeah. I'm sure.
And number 9A and 9B.
Oh, but they're all simple sentences.
Well, if I said it's invalid, number 9B is invalid, that the two numbers are rational. The sum of the rational, the converse is not necessarily true.
Correct. Right. That's a converse error.
So I got it, right?
Yeah. Cool.
Hmm.
You can add two irrational numbers together and come up with a rational number.
Yeah.
So for example, what's a really common irrational number?
Pi.
Yeah, pi.
Right, yeah.
You add pi, which is irrational, to negative pi, which is also irrational, you get 0, and 0 is a rational number.
Oh, okay. Okay. Number 6.
6. Number 6. Oh, yeah. Well, we did one like that. I just changed the letters.
So should I say it's valid?
I'll have to check on that one. I don't have the answers in front of me, but.
I saw that too.
Michaela, you have invalid also?
I had valid.
Valid, that's what I said.
Oh, okay. So 2 of you had valid?
Yeah.
Oh, then it must be right. If everybody comes up with the same answer, the answer must be correct, right? Yeah, we'll go over these a little bit. And so there's lots of ways to answer. There isn't any one right way to answer. Well, a couple of them there are, but a lot of them, there's different ways to approach it, different ways to answer it. So, yeah. Well.
Then O and OO.
Oh, so the without examples made that a little difficult, didn't it?
Yeah, but I said the equals means that that two things are exactly the same in the value.
Okay.
It refers to object. Equivalent means that two arguments are logically the same, not necessarily exactly the same. It refers to the statement.
Well, that's kind of an example. So equal actually means identical. We use the equal sign often when we can't. So for example, is 5 plus 3 equal to 8?
5 plus 3 is 8, yeah.
But is the left-hand side of this equation identical to the right-hand side of this equation?
No.
No. This expression, this equal sign, is not correct.
True.
So if I put the third, so this statement, as you see it right here, is technically false. If I put the third line down here, oh, wait a minute, let me start the recording. So we're a little off time. If I put, so 3 means equivalent.
Yes.
These are equivalent because the value of the left-hand side is the same as the value of the right-hand side.
True.
But these are not equal. On this side of the equal sign, we have a 5, a plus sign, and a 3.
Okay.
Side we have an 8. They're not identical, but they are equivalent.
Yes.
Yeah. So we often use the equal sign in a casual way that's not precisely correct. So equal just means identical.
Okay.
To object equivalent means they have the same characteristics for whatever you're discussing, right?
Yeah.
So your your social security number is equivalent to you, but it is not you.
True.
Okay.
That makes sense. I did good in the test then.
Yeah, I'm sure you did. All right. Something completely different for a while now. All right. I mean, there's still going to be a whole bunch of if-thens in there. So today we're going to start something that's very, very simple and has global impact on it. So let's start with a really simple example. So today is Wednesday. That statement true or false? Silence. Is that statement true or false?
Today is Wednesday.
So that's
It better be true.
it's true. Yeah, that's what I feel.
well, but without any other context, is it if we are in, for example, if we were on the other side of the planet, it might not be true.
True.
Tomorrow, that statement will be false. Yesterday, that statement was false. So a little bit of philosophy here. Truth can change. Something that's true now can be not true later, right?
Yes.
So true can be a moving target. So in mathematics, we have things called theorems. A theorem is something that's true all of the time, always, never, ever, ever false. So it's an absolute kind of truth. So truth you can have absolute truth and you can have conditional truth, right? But anyhow, that's beside the point. Okay, so one, what day will it be? So what day will it be in 5 days? Assuming this is true, what day will it be in 5 days?
Monday.
Will be Monday. Took you a long time to count that one up. So in 5 days, it will be Monday. What day will it be in 9 days? What day will it be in 9 days? I can almost hear you counting. What day?
Wednesday?
In 9 days, it will be Wednesday?
No, my bad. Sorry.
Friday.
Friday, yeah.
Oh, okay.
Yeah, Monday to Monday is okay.
Sorry to ask you such hard questions first. Jeez. What day will it be in 873 days? So 873 days from today, what day will it be? Oh. Now remember, good math requires that you be very, very lazy. What's the wrong way to probably try and answer that question?
Count 873 consecutive days.
Yeah, to start counting, break out a calendar, 1, 2, 3, 4, 5, and we'd probably all get it wrong, right? So, well, here comes the key for what we're doing today. So, from now, go forward 873 days. So that's the question, right? Now being Wednesday. All right, let's be really lazy here. Today is Wednesday. What day will it be in 7 days?
Wednesday.
What day will it be in 14 days?
Wednesday.
What day will it be in 700 days?
Wednesday.
What day will it be in any multiple of 7?
Wednesday.
So if we started to count 1, 2, 3, 4, 5, every time we get to a multiple of 7, we are back at Wednesday. So let's be lazy. Let's pull out all of those multiples of 7. How do we pull out multiples of 7 from 873? What elementary arithmetic operation will pull out groups of 7? Starts with the letter D.
Just divide by 7.
Divide by 7. So if we divide 873 by 7. Okay. And because every 7 days, we are right back where we started again. So 8 goes, that's 1. Here comes arithmetic. Tell me if I make a mistake. 7, we subtract, that gives me 173. 7 goes into 17 twice, that gives me 14. We subtract, that's 33. 7 goes into 33, 7 goes into 33 4 times, right? 4 times 7, 28. We subtract. 33 minus 28 is? 5. Okay. So to go forward from Wednesday 873 times, we will have hit Wednesday 124 times. And then we would go 5 more. So Wednesday plus 5 is what day? This is the first one I asked you.
Monday.
Yeah. So the answer is Monday. So 873 days from today, it will be Monday. Done in less than a minute. Aha. So now, this little simple, lazy way of counting ahead, when you are in something called a module or a cycle, a module, eventually, if you go forwards or backwards, you get right back to where you were. So let's try another little example here. And we divided by 7 because there are 7 objects in that module, the days of the week. So right now, it is February. What month will it be 3 months from now? So in 3 months from now, it will be
May.
May. Okay. What month in 11,341 months? Well, we certainly don't want to count, do we? But if we started counting, when would we be hitting February?
12 months.
Every 12 months.
Every time we count to a multiple of 12, we're right back at February again. So why waste all that effort when we can pull out all the groups of 12? So our February is part of the months of the year. So our module has 12 objects in it. So multiples of 12 bring us right back to where we are. So we would divide 12 by 11,341. So this goes in 9 times, right? 12 into 113. So 9, that's 8. 9, that's 18, 9, 10, 108. Did I do that right? Is 9 times 12 108?
Yes.
Oh, good. I'm terrible with this stuff. 113 minus 8 is 15. 41. 12 goes into 15 once. It's 12. That gives me 341.
Wait, I think it was just 5 for 113 minus 108.
What? Oh, yeah.
Yeah.
Thanks. Yeah. I can't do arithmetic. That's all right. Let me see. So where am I here? Oh, so yeah, 12 goes into 54 4 times?
4 times, yeah.
4 times, so that gives me 48. Subtract, so 48 to, that's, I think, 61, right?
Yeah.
12 goes into 61 5 times, 60, subtract. We have a remainder of 1, so it will be March. So 11,341 months. If we start counting, we will come to February 945 times, and we'll have 1 left over. So February, add 1, we get to March. 11,341 months is 945 years with a remainder of 1 month. So that seems pretty simple, right? It's a very fast way to compute all of that. So these last two examples with day of the week and month of the year, every time we send sensitive information in any kind of digital form. So when you type in your credit card number, when you're buying something on the internet, when you send bank information back and forth between you and your bank, you want to check your account balance, you have to log in. That sensitive information is going over the internet. When the military communicates with their forces all around the world, so in Washington, they're talking to somebody on an aircraft carrier, they're sending really sensitive information and you don't want anybody else to see it. It all gets encrypted so that it just looks like gibberish to anybody who sees that message. The encryption scheme that keeps that safe is all based on what we just did right here. This simple idea of dividing by a number and using that remainder to find out where you are is what keeps all of that stuff safe. Now, some of you who are in computer science, so we're talking about encryption and cryptography here. You may have heard of things like RSA codes or public key encryption. It's all based on this simple idea of dividing by looking at a remainder. So what we're going to be doing for the next so many classes is based kind of on this. And the fancy title for this is Modular Arithmetic. So modular refers to a closed system of objects, like days of the week, months of the year, hours on a clock, 26 letters in the English alphabet. So those are modules. If you start counting in the English alphabet, if you start with B, you know, what letter, if you keep counting ABC all the way up to Z and then come around to A again, starting with B, what letter would be 900 letters down that chain? And it would be another letter. In this way, we can encrypt regular English words into just numbers that nobody else can figure out what it is. So here's a definition. There's other definitions. This is the one we're going to use. If. Well, here's a definition. We do it this way. And this is pronounced. So everything here is integers. So A and B are integers. And this little symbol here, we've seen that before. That means belongs to. So A and B are objects that belong to integers. What's an integer? It's a kind of a number. What's an integer? What kind of number?
A whole number, positive or negative?
Yep, an integer is any whole number, positive or negative. So -2, -1, 0, 1, 2, 3, and they're infinite here. So that's an integer. And n has to be greater than 1. It should say, sorry. So n, a, and b are all integers. A and b can be anything, but n has to be greater than 1. So 2, 3, 4, 5, 6, 7, 8. Right? So here's how this is pronounced. In this case, that's the symbol for equivalent, but in terms of modular arithmetic, we read that as congruent. So congruent means equivalent. So A is congruent to B mod n. That's a definition of structure here. So we go with the definition. So if A is congruent to B mod n, then A is equal to B plus Kn, and K is also an integer. So it's this structure that we're going to use to do modular arithmetic here. And there's some other kinds of things we're going to do today. So this is the formal sort of math looking stuff on here. So let me give you a couple of examples. So we know, so let's say, oh, I forgot what I was going to say. Hang on a minute here. So let's go here. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. All right, so n, for this example, n is equal to 7, and n is called the modulus. The modulus, n, is how many things you have in your closed cycle, your closed module. There's 7 days of the week, so n is 7, and so n, the word for that is the modulus on here. So I'm going to change these letters into numbers. So I can number anything I want. I have to start with 0. That's required. And once you pick a 0, you have to number things in order. So I can put a 0 anywhere I want here. So I'm just going to start here. So 0, 1, 2, 3, 4, 5, 6. And if I kept writing, the next letter here would be Monday. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday, Tuesday, and we keep going. So next would be 7, 8, 9, but I don't need those because Monday goes back to 0. So from Wednesday, go forward 93 days. And what day of the week will be at? So what we're asking here, so let's do this the old way. So every time we count to 7, we're back at Monday. So we're going to divide the 93 by 7. So 7 goes into 93. That's once, that's 7, that's 23, that's 3, that's 21. We subtract and we get 2, which is Wednesday. So starting on a Monday, if we go forward 93 days, we'll hit Monday 13 times. In other words, 93 days is 13 weeks with 2 left over. So we'll hit Monday 13 times, and then we'll have 2 days left over. So 1, 2. So we have Wednesday. Okay. So that tells me a couple of things. So that's sort of an example here. Now I'm going to put it into this form. So we can say, so we went from Wednesday, we went forward 93 days, and we ended up at Monday. So Wednesday, Monday. Whoops, sorry, I did that wrong. Wait a minute. 93 days, go forward 2, 95. Well, wait a minute, hold on. I messed up somewhere. We started at Wednesday.
I think when you were writing it, you were talking about it where you were saying you changed where you started from to Monday, and that made the result we ended on Wednesday, but it was written down we started on Wednesday, so I think the result would have been Friday.
Oh, so let me try that again. From Wednesday, go forward. I got my days mixed up. Go forward 93 days. All right. Oh, so we divided by 7, we had a remainder of 2, right? So that would be Friday. Yeah, you're right. Sorry. Okay. Yeah, we started at Wednesday. So I kept saying Monday, you're right. So we started at Wednesday here. So Wednesday is 2. Go forward means add, and we ended up at 4. So from Wednesday, we went forward 93 days, and we ended up at Friday. So we find that 95 brought us to 4. 2 plus 3 is 95, and we ended up at 4. So going back to this notation up here, we find that 95 is congruent to 4 mod 7. Wait a minute, let me just make sure I did that right here. So let's do 7 into 95. I think I might have messed up the days again. This is not that hard. Don't think because I'm messing up second grade arithmetic here. So 1, 7, 25, 3, 3, 21, 4. Yes. All right, we're good. Yeah, that's correct. So 95 is congruent to 4 mod 7. So this is just abstract, but this is an application of that. So in other words, equivalent. In our days of the week example that I'm doing here, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. 0, 1, 2, 3, 4, 5, 6. So in terms of our closed system of days in the week, 95 and 4 both represent Friday. So so 95 and 4 both represent the day Friday. So now instead of saying Friday is 4, I can also say Friday is 95. So I can hide that Friday with a couple of different numbers here. So there's some properties that come up on here. So another way to look at this will often be, in fact, if I add 7 to 4, I could also say that 95 is equivalent to 11. I can just keep adding multiples of 7 to this number, or I can keep adding multiples of 7 to this number, and I'm still going to have numbers that are congruent to each other. And that hints a little bit at how we can hide words by changing them into numbers and encrypt them using this system here. So a lot of times what we're going to want to use, we're going to want to look at B here. We're going to look at something called least positive residues. Fancy name, least positive residues. The least positive residues are the set of positive integers the set of non-negative integers What's the difference between non-negative and positive? The subtlety of the word.
Non-negative includes 0.
Correct. So we're looking for the least set of non-negative integers, 0, 1, 2, ... all the way up to n minus 1, where n is the modulus. In other words, so that's the fancy way of saying it. The least positive integers are the remainders you get when you divide a by n. So I'm going to give you an example of that. So for example, let's let n equal 6. This is the modulus. When you divide by 6, what are the only possible remainders you can have? So when you divide by 6, the only remainders are 0, 1, 2, 3, 4, 5, all the way up to 1 less than 6. When you're dividing whole numbers by whole numbers, the only whole number remainders you can ever get are 0 all the way up to 1 less than number. So when we're working with a modulus of 6, these are the least positive residues. So just think of least positive residue as the smallest remainders that are not negative. So for example, so 15, so 57 is congruent to what? Mod 6. So to answer this, so it's like an equation, so we would just do 57, whoops, sorry. We divide 6 into 57. So that goes 9 times, that gives me 54. That leaves me with a remainder of 3. So 3 would be the least positive residue here. There's actually an infinite number of solutions to B, but they're all equivalent. You just keep adding 6 to this and you're going to keep getting valid congruences here. So why use bigger numbers when the littlest one will do? So we're going to be mostly concerned with the smallest non-negative remainders whenever we divide by n. So looking at this, we see that, so 57 is equal to 6 times 9, whoops, sorry, 57 is equal to, wait a minute here. Yeah, is equal to 3 plus 9 times 6. So 9 times 6 is 54, plus 3 gives me 57. So that's another way to write this division down here. So another example of mod 6. So if we wanted to know 103 is congruent to what? Mod 6. There are an infinite number of solutions here, but we want the laziest one. So the least positive residues are the laziest whole number remainders that are not negative. So we would do 6 into 103. That's 1, that's 6, that's 43. 6 times, that'd be 6. That would be 36. 43 minus 36. Oh, I didn't go in enough, did I? That would be 7. That'd be 42. Subtract would be 1. So this answer could go here, and we see that 103 is equal to 1 plus 17 times 6. So these are alternate ways of saying all of this. Now, I know a bunch of you have some computer programming background. I think if I wrote this symbol, the percent sign, is that familiar to anybody? That's the symbol for mod.
Yeah.
Ah, there you are. Well, there it is right there. That's the mod, right? So 57 with a modulus of 6, you do the percent sign, you're going to get a 3 return. If you're working with a modulus of 6, you type in 103, the percent sign, you're going to get 1 return. So this is the mod. This other number here is called the div, D-I-V. So this is div and this is mod. I don't know what the symbol for div is. I only know that the mod is the percent sign. So some of you kind of already know what this is, but maybe you haven't seen it in this form before. All right, so structure. So an algebraic structure. It's the structure that we're going to use to prove things here. Just like when we did argument analysis, we don't care about the words, we just care about the structure of that argument. So if A is congruent to B, mod n, then A is equal to B plus K times n, where K is an integer. So this takes it from a definition of something that's not regular arithmetic and puts it into something that is regular arithmetic. And it's that's going to allow us to prove some properties of this congruences here. Now, there are other ways to say this. So this is equivalent, or we can also say that A and B have the same remainder when divided by n. These two, all three of these statements, this one, and this one, are equivalent. They all say the same thing, just in a different way. So they're not equal, but they're equivalent. And it's these properties that are going to allow us to look at, like I said, encryption schemes. How do you hide information from anybody except the person that you want to see that? So there's some properties that we'll be going through on there. So before I play around with a little, oops, sorry. I'm sorry, I'm looking something up here and I just jumped way to where I didn't want to be here. Well, I'm trying to find that page again. Does anybody have any questions yet? Comments, questions? Whoa, hold on. I'm totally lost where I am here. Whoa. There we are. I hit this digital textbook is so sensitive to touch. All of a sudden you jump 500 pages and you don't know where you are anymore. So let's see here. Just give me a second. Hold on, almost there. Well, let's do some examples. Let's play around with it a little bit. Let's just make some conjectures about some things here. So let's work mod 11. Now, important to us when we start looking at how we hide things. So eventually I'm going to be sending you email that looks like just a string of numbers, and you're going to be able to read it and answer that question and send me back a string of numbers, and nobody but us will be able to read this. So one kind of thing that's really important when we're doing all of this is our modulus needs to be a certain type of number. So for example, it's always going to be an integer, but 11 has two characteristics. 11 is what kind of number? I mean, it's an integer, but what kind of integer is it? It's
Odd.
It's odd. It's also what else?
Prime.
Prime numbers. Prime numbers are very, very important in all of this. So what's the exact definition of a prime number? Prime number definition has exactly two divisors. And those two divisors are 1 and itself. And the word exactly is important here. So 1 is not a prime number. 1 only has one divisor. 2 is the only even prime, because 2 can only be divided by 1 in itself. All other prime numbers can't be even because then they have a divisor of 2. So prime numbers are very important. So 2, 3, 5, 7, 11, 13, 17, 19. What comes next?
23.
3. What comes next?
29.
29, right. How many prime numbers are there?
Infinite.
How do we know that? How do you know they're infinite? How do you know there isn't a biggest prime number somewhere? Oh, eventually I'm gonna prove that to you. The prime numbers are never ending, and we're gonna prove that eventually by assuming that there is a biggest prime number and then show that that can't be true. So the prime numbers go on forever. So the interesting thing about the prime numbers, so this is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth. This is the 10th prime number. If you wanted to know what the 15,000th prime number is, what would you have to do? You'd have to go find somewhere to look it up. There's no way to predict. So some of you have had Calc 2 already. I know some of you are in it. But in Calc 2, when you did series and sequences, if there's a pattern to a sequence, you can come up with a little formula and predict what the 900th term in that sequence is. Prime numbers, there is no known formula for predicting what the 800th prime number is. You actually have to just work it out. The curious thing about prime numbers is, and what makes them so safe for encryption, is nobody's ever found a pattern to this sequence. So here's a sequence with a pattern. So 3, 9, 27. What comes next? 3, 9, 27. What comes next?
54.
Nope. What comes after 27?
81.
Oh, 81 comes after 27. What comes next?
243.
Nice, 243. Okay. So this is 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, 3 to the fifth. So if I wanted to know what the 11th number out there was, you would just do 3 to the 11th. This sequence has a pattern. No one has ever found, and when I say ever, humans have been looking for the pattern to prime numbers for about 3,000 or 4,000 years. 3,000 or 4,000 years ago, people wondered, is there a pattern to the prime numbers? And the answer is, nobody knows. Nobody knows if there is a pattern. Nobody knows if there is no pattern, and it's completely random. And it's that inability to determine a prime number that makes the encryption stuff that we're going to work on relatively safe. So there's a big issue here. It's been forever and forever and forever. Now, so prime numbers are important when we're doing modular stuff. So let me show you an example of why. Let's do, remember when you were doing times tables in grade school? I don't know if they still do times tables or not. People try to find a way not to have to like think or memorize anything. But I remember in grade school, we had to memorize the times tables all the way up to 12 times 12 is 144. Anybody else have times tables?
Yeah, we had those.
Yeah. Our teacher promised us, well, I think I was in like maybe 4th grade, maybe 5th grade. I don't remember. Said as soon as everybody knew their whole times tables all the way up to 12 by 12, we would have like a picnic outside or something. I was the holdout. I was the last one to memorize them all. So let's do times tables. Only we're going to do a times table mod 5. So we're going to do over here. So multiply, and I'm going to put a 5 there for mod 5. Now, 0 times anything is 0, no matter what mod system, even regular. So I'm not going to use zeros. I'm going to use the non-zero residues of 5. So, oh, hold on just a minute. Somebody's at my door. Hang on. Oh, thank you. Oh, I thought I had a visitor. I just got a package, no big deal. So when we're dividing by 5, the only remainders that are not 0 are 1, 2, 3, and 4. We put 1, 2, 3, 4 down here again. Now we're going to multiply mod 5. So hang in there with me. It's about to get strange. Well, first of all, and we go in this direction. So 1 times anything is itself. 1 times 1 is 1. 1 times 2 is 2. 1 times 3 is 3. And 1 times 4 is 4. Good. Now let's do 2. 2 times 1 is 2. Oh, somebody said, what'd you do in math class in college today? You can say we did times tables up to 4. How about that, huh? 2 times 2 is 4. And what's 2 times 3? 2 times 3. Oh, nobody's answering. What's 2 times 3?
6.
Yeah, but we don't have a 6. It's 1. 2 times 3 is 6, but when we divide by 5, we get 1. Remember, this is the mod 5 table. So 2 times 4 is 8, but divide by 5, and what do you get left over?
3.
3.
3, yeah.
Hey. So what'd you learn in college today? 2 times 4 is 3. Oh, that's what you get for going to a community college, huh? All right. 3 times 1 is 3. 3 times 2 is 6, but divide by 5, the remainder is 1. 3 times 3 is 9, divide by 5, and the remainder is 4. 3 times 4 is 12, divide by 5, and the remainder is 2. Now we go on to 4s. 4 times 1 is 4. 4 times 2 is 8, divide by 5, that's 3. 4 times 3 is 12, divide by 5, that's 2. And 4 times 4 is 16, divide by 5, and 1. So that's the times table, mod 5. And you can see why we don't need 0 here. Now notice, 5 is not only odd, but 5 is also a prime number. So our set of numbers, if we're working in mod 5, if we're multiplying in mod 5, that's all we have. That's like a 4-day week, right? Talk about any day of any week, it's going to be Monday, Tuesday, Wednesday. So this is all we have. Now notice on every row, every one of these numbers shows up exactly once. In every column, every one of these numbers shows up exactly once. Kind of like one of those Sudoku things, which I really hate, by the way. So 5 is odd, 5 is prime, and every number shows up exactly once in each row and column. Okay, I'm going to do another times table here. Now, we're going to work mod 6. So mod 6, 1, 2, 3, 4, 5. Those are the only numbers that exist for us, mod 6. All right, fill it out. Now, 1 times anything is 1. So 1 times 1, 2, 3, 4, 5. Okay, now we multiply by 2. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is what? So 2 times 3 is, well, what is it really?
It's really 6, but would it be 0?
Yeah, 2 times 3 is 6. Divide by 6 and you get a 0. Uh-oh, we don't have a 0. 2 times 4 is 8. Divide by 6 and you get a 2. 2 times 5 is 10. Divide by 6 and you get a 4 as a remainder. So here's what happened. 1, 3, and 5 are missing. We have the 0 that we don't even have. And the numbers 2 and 4 showed up twice on that row. Well, let's try threes. 3 times 1 is 3. 3 times 2 is 6, divide by 6, remainder 0. 3 times 3 is 9, divide by 6, remainder 3. 3 times 4 is 12, divide by 6, you get 0. 3 times 5 is 15, divide by 6, and you get 3. So that row is even worse. Go to fours. 4 times 1 is 4. 4 times 2 is 8. Divide by 6, you get a 2. 4 times 3 is 12. Divide by 6, you get a remainder of 0. 4 times 4 is 16. Divide by 6, you get a remainder of 4. 4 times 5 is 20. Divide by 6, you get a remainder of 2. Fives. 5 times 1 is 5. 5 times 2 is 10. Divide by 6, remainder 4. 5 times 3 is 15. Divide by 6, the remainder is 3. 5 times 4 is 20. Divide by 6, the remainder is 2. And 5 times 5 is 25. Divide by 6 by 1. Oh, all the numbers came out here. 5 and 6 have no common factors. All the numbers shows up. How many times does 2 go into 6? 3 times, and we get 3 different digits here. 3 goes into 6 twice, and we get 2 different digits. 4 goes into 6 in common factors. So when you have a mod that's even or not prime, you have wonky things happen. You get the number 0, which isn't even in your set of allowed numbers here. And so if you were doing an encryption scheme here, 1 and 3 turn out to be the same thing. 2 and 4 turn out to be the same thing. So prime integers are very, very important because your remainder is unique. When you divide by 6, you get repeating remainders over here. So that's some of the crazy stuff about modular arithmetic. So for homework tonight, there's going to be just sort of getting used to this whole idea. Some of the homework's pretty straightforward. Show that these two numbers are both congruent to each other, mod something or other like that. And let me see if I can just pull one up here. So this is a lot different than the logic stuff, right? This is a nice little change of pace. For those of you who are doing computer science and all that, this modular stuff, the div and the mod, they get used as a method to multiply really huge numbers together. Like a number that has 15,000 digits in it, multiply that by a number that has 12,000 digits in it. That can burn up a lot of processor time. So by reducing things by modular congruence, that multiplication can happen much faster. Let's see here. Well, I can't find any right now. So some of the things that we're going to do, let me come back. So this modular stuff shows up all around us. If I were to give you this, so clearly you know what I just wrote down. What is that? I got it from the back of a book.
Barcode.
Not a barcode, but that's the ISBN for that book. International Standard Book Numbering. So you really can't say ISBN number, because that's the word number. If you say ISBN number, you're saying International Standard Book number. This identifies this book uniquely from all the other books in the world. So this is like an area code. The 978 doesn't mean anything. This is 13 digit. because there's 13 digits here. ISBNs used to be only 10 digits big, and then we ran out of numbers. So they had to slap this in front of it here. This is like an area code. I know some of you might be old enough to remember if you wanted to call somebody in your neighborhood, you only had to dial 7 numbers. And then we ran out of phone numbers in the country. So now you have to dial all 10 numbers, even to call somebody across the street, assuming you even have a landline anymore. So this is the publisher, this is the language that the book is published in. 1 means American English. 0 also means American English. This is the publisher of the book, which in this case is this is Brooks Cole. This refers to the actual book itself, the edition and all that. But where modular numbers come in here, this last number, this is a check digit. Driver's license have it, credit cards use it. So these first 12 digits, those are created by humans. This last digit is created by a computer doing a modular arithmetic algorithm based on all of these digits. And this check digit applies so that when you're typing in a book order, it's very common for people when they're typing in a long string of numbers to get one number wrong. They'll type, instead of 37, they'll type 73 or something like that. The check digit will catch that mistake and say, no, the number you entered is wrong. Sometimes when you swipe a credit card or something at the store and it'll say invalid, do it again, there may have been a glitch in the transmission, like a couple of zeros and ones got switched around, so the check digit corrects it. How that number is computed is done by a modular arithmetic thing that I'm going to show you in the next class. Somebody also mentioned barcodes, the UPC codes that you see on the back. Somewhere I have a UPC code. Maybe I don't have a UPC code. Oh, here we go. So the UPC code that you see on things, the laser reads those black bars, but they're represented by those digits that happen underneath. That last digit way over on the end is also a check digit done by a modular arithmetic algorithm. So I'll show you some of those when we get back together on Thursday. So brand new topic.
Monday.
What?
We don't have class tomorrow, on Monday.
Oh, today's Wednesday.
Yeah.
Oh, yeah, Monday. I was, for some reason, thinking today was Tuesday. I don't know why I was thinking that. Yeah, so on Monday, I'll show you how some of that stuff works. So brand new topic for a little while. There's still some logic in here. There's still some if-thens and that sort of thing. So questions, comments, anything about this? It's just a nice change of pace, right? So I will work on the tests today, and I will do my best to get them done for you by later tonight. I have another class right after this one. I also have 3 other classes that have submitted tests in, so I got like a whole lot of grading to do, but I'm going to work on yours first. I finished the Calc 2 stuff yesterday. I'll work on yours today, and I guess that's it for now. I'll get some homework up. So we're in section 8.4 of the textbook, by the way, of the one that I've uploaded. If you have the hardcover textbook with you, I think we're in chapter 10, but the one that I've uploaded to Canvas is up there. So anybody got any questions or comments or any questions about the test? I know we talked about a couple of the answers on the test. Anybody have any burning issues that they're wondering about the test until I get them all graded? So we decided for the Alice in Wonderland one, it was the dodo telling the truth, right?
Yes, I'm very sure about that.
Yeah, no, that's correct. And I forget what else you were asking me about that.
Yeah, you said you were going to go through it in the next class.
Yeah, I just wondered if anybody had something they just really needed to know right now because they can't wait anymore. I know that happens. All right then. So have a great weekend. I think it's going to be back in the 50s again or something. So good time to get outside for a while.
Yes, in the 50s. It's beautiful.
Yeah. So I'll see you all back here on Monday.
Right.
Nice week.